So this in your book, that's theorem 3.11. So these are now properties of these vectors, and it's very similar what you saw a long time ago in section, I think it was 1.3, when we talked about algebraic properties of matrix addition, subtractions, and scalar multiplications. So in the following, we do U, V, and W are 3 vectors, and alpha and beta are numbers. Then the following things are true. One is U plus V is the same as V plus U. So for the movement, it doesn't matter which vector you move first and then the other vector or the other way around. Part B, it's again associative. So if you have 3 vectors, how you add them doesn't matter. You can add them in any way you like. So that essentially this means you don't need parentheses. You can do whatever you like, not just with 3, also with more. You can do this. If you heard about induction, that's what it is. Then if you add the 0 vector to another vector, which is the same, you always get the vector back. So the 0 vector is like the 0 movement. No? It means don't move. So you go along the vector and then don't move. And that's the same as the vector itself. Then if you add the inverse vector to a vector, you get the 0 vector. So it means every vector has an inverse vector. Part E and E, F, and G, they're all kind of distributive law now. If you do alpha times U plus V, you can actually distribute the alpha. If you have 2 numbers, alpha plus beta times U, you can distribute the vector. If you have 2 numbers multiplied with the vector, you get this. So it means it's associative also again, these 2 numbers and a vector multiplication. And finally, that's an important one. If you multiply a vector with the number 1, the vector doesn't change. Okay, so, and as I said, everything is kind of clear based on how we define this now. So this is also a theorem. Later on, we will flip. We say, whenever there's an object which has these properties, we call it a vector space. So that will be in chapter, also section 4.1. So when suddenly we flip things around and say, okay, whatever behaves like this, we call them vectors. Even they're not vectors in this sense. Also in the sense that it's just n numbers. They can be other things, and you will see other examples for vectors in chapter 4. Okay, and another easy consequence out of this is the following. This is theorem 3.12. Again, we have U in Rn and alpha in R. Then A 0 times V, so this is the 0 number, is the 0 vector. So 0 times any vector is always 0 vector. The next thing is, if you take any number and you multiply it by a 0 vector, you get the 0 vector. So this is a 0 number, this is a 0 vector. And finally, if you multiply -1 times a vector, you get the inverse vector. And now can you say, why did the book not put these up here? The reason is later on, we will say if whatever behaves like this, so we're asking for these properties, is called a vector space. And then these down here are a consequence. So based on this, you can actually show this. And that's the reason why our book puts them in 2 different let's say, sections or two different theorems. And yeah, so this is the reason why it's split like this. For us, because for us in the moment, keep in mind, if we talk about this, going back to the previous paper, a vector is always just this. So all these things are kind of clear in the moment you look at what are these actually? Oh, these are just sets or sequences of numbers. No? Okay, and then one more definition. And this definition, again, we had already for matrices. It's the definition of a linear combination. And after this, we make a picture for this, and then it shows actually what is actually different in this section compared to the section in chapter 1. So